right, folks, here we are. It's actually the day of your test, or the eve of the test for another period, for a third period. And I'm sitting here with a couple of cramming calculus kids. And it's 3.4 concavity and second derivative test. So if you want to look at, we're just going to take this as far as we did at 3.1 and 3.3. So if this is f of x, or y, whatever you want to call it, let's call it f of x. All right, and we want the derivative of f of x. We get 9x squared minus 9. No problem. All right, that tells us our relative mins and maxes, just to review. So it's going to be 9 times x squared minus 1, and that would mean that we have 1 and negative 1, and we'll have to test. And we're going to test in the first derivative. We're going to do our sign analysis in the first derivative. I don't know why I put these here. Usually, I put slash marks at the numbers. Yes! So, let's test 0. When you plug in 0, it's negative. When you plug in something negative, like negative a million, oh yeah, it's positive. When you plug in a million, it's positive. So we will notice we have a relative max at negative 1, 7. And we'll have a min at 1, negative 5. All right, so we have relative max here and a relative min here. So far, so good. That's all review. Remember, we have to write down everything we have with some types of English words. Well, if we want to talk about the concavity, and this is new stuff, so I'll do it in red. I want to talk about the concavity of this thing. What we're going to do is we're going to take the second derivative. So to find concavity, we take the second derivative. Second derivative of this is just 18x. And then we're going to set that guy equal to 0. And then we're going to do another sign analysis, and that's going to tell me where it's concave up and concave down. Just like plus and minus told me where the original graph was increasing and decreasing, now doing the second derivative and almost mirroring what we did the first derivative, that's going to tell me the concavity. Plus means concave up, minus concave down. So let's try it. We're going to set this guy equal to 0, so I get something called a poi. All right, and that's nothing you eat. It's just called poi, and that's called a point of inflection. Point of inflection actually means that you might have a possible, or I don't want to say possible. Point of inflection is a change in concavity. So we're going to do a sign analysis, and our sign analysis is just at 0. So we're going to look before 0, after 0. It's clear that when we plug in a number like negative whatever, a million, into the second derivative, and we're going to plug into the second derivative, we plug a negative, we get negative. When we plug a number before 0 into it, we get a positive. So I would write this. F of x is concave down. Sometimes I just do CD. Concave down, CD, on negative infinity to 0, not inclusive, because the second derivative of x is not greater than, it's less than 0, and f of x is concave up. Concave up on 0 to infinity because, because, why? Because the second derivative is greater than 0. If it equals 0, by the way, it's inconclusive. We don't know. All right. So it's less than 0 equals greater than 0, blah, blah, blah. We're good. And we have a point of inflection. At, and I'm going to say it's 0, comma. Well, remember that this comes from the original. That comes from the original equation. So when I plug in 0 into the original equation, it was plus 1 at the end. So that is our point of inflection. Any questions? No. Okay. That's how you find points of inflection. Just like that. All right. I have another one planned. Here it is. Okay. So now we're going to find the second derivative. So the first derivative, got to find the first derivative, find second derivative. First derivative is 2x to the negative 1/3 power. That's 1/3 minus 2. And then we're going to find a second derivative. I haven't moved it yet because I'll move it at the end. And the second derivative is now going to be negative 2/3. And then this is going to be x to the 4/3 power on the bottom. Remember, that goes to 0. So now we're going to set this, where can this be 0 or undefined? Okay, this could be undefined at 0. So once again, 0 is an issue. All right, 0 is an issue. So now I'm going to check the signs to the left of 0 and to the right of 0. So to the left of 0, when I put in negative whatever, okay, well, we got a problem. I think we got a problem because I can't put a negative inside. Oh, it's a cube root. I'm good. Cube root's good. So I'm going to put a negative in, I get negative. When I put a positive number in, like a million, I get negative. Uh-oh. There's no change in the sign. There is no change here. If there's no change there, that means that there's no poi. So it is possible that graphs don't have points of inflection. Think of a line. A line doesn't have a point of inflection. All right. So not every graph will have a point of inflection. I want to thank Mr. Burns for helping me discover this next thing. Check this out. All right. Let's give it a function example. Let's give a function like 17x squared. Let's go cubed. 17x cubed minus 3x squared. So we want to find critical numbers. Critical numbers, you take the derivative and you do what you do. Do what you do. 51x squared minus 6x. Factor that. Set it equal to 0, I guess. And you're going to get x, and it's going to be 51x minus 6 equals 0. So you're going to get critical numbers at 0, and then it looks like 6 over 51. All right, 6 over 51. So we're going to check numbers in between. All right, and we're going to say, all right, to see if it's a max or min. Well, if we go negative, if I put in like negative 1, this becomes positive 6. This becomes 51. It's positive. If we check in between 6 over 51, I would probably pick like, I don't know what 6 over 51 is, but I'm going to guess it's pretty small. So I'm going to pick something really, really small like 0.1. If I put in 0.1, it's still positive. If I pick something like a million, it's still positive. Oh, crap. There's no critical numbers on this one. All right, I got to make up another question. All right. Let's get one that has some critical numbers. Hold on. That's why I bring my notes, just in case. Just in case things get crazy. Here we go. Ones that have critical numbers. Like this one. Of course. Of course. X cubed minus 3x. Sorry about that. Minus 3x squared plus 3. F of x equals this. So then again I go f of x equals f prime of x equals 3x squared minus 6. Now now I set that equal to 0. I get 3, and then I get x squared minus 1. No, minus 2. Oh no! All right. God forbid I pick one that is nice. All right. Well, this equals 0, so I get critical numbers of square root of 2 and negative square root of 2. Just what I wanted. So when I put in 0, it's negative. When I put in something very negative, it's positive. When I put in something, this is very positive. So I have, if you agree, I have this one's a relative max, and this one's a relative min. And max because it goes from positive to negative, this one goes from negative to positive. This is what I found out. If you go into the second derivative and use these points, so if I plug this in to the second derivative is going to be 6x. If I put that in and I get something that's negative, that automatically means it's a relative max. And if I put in the other one and I get something positive, that means it's a min. So I can use the second derivative test to also, this second derivative test, to see if it's a max or min without using that. The only thing I need to know is what the possible critical numbers are. How great is that? And it always works. So that's pretty cool stuff, I think. I think so. So we have max, min. Now we know if we plug it in, it's a max, plug it in, it's a min. But let's talk about poi. Let's do another one for the poi, because you know what's coming up? I feel it. Trig. We got to do a trig one. So now for poi, it would just be f double prime of x equals 6x. And then 0 would be my possible point of inflection, possible point of inflection. I'm right. Okay. So we check the left, it's negative. Check the right, it's positive. So it goes from negative to positive. Watch the hands. Watch the hands. Okay. Goes from concave down to concave up, like that. Did you see it? Watch. Concave down, concave up. So that's what's happening. That's a point of inflection, and I believe it's 0, comma. Let's go to the original. Back to the original. 0, comma 3. So 0, 3 is a point of inflection. Cool? Not too hard stuff, I'm telling you. Last one. I want some trig. Hold on. Our last problem is going to be y equals cosine x minus 1/2 cosine 2x on the interval 0 to 2 pi. Being a cyclic function, we're just going to take one cycle. So now we're going to take the derivative, which is now professionally done by you. Negative sine x. And this is going to be plus sine of 2x. You might say, well, where did all the stuff go? Remember, it's negative sine minus a negative sine is positive sine, and the derivative of the inside is 2. 2 times 1/2, it goes away. Got all that? So when is this 0? We have to find out when this guy is 0. Well, this is a trig identity. That'll help us. This is going to be negative sine x times 1 minus 2 cosine of x. And then we'll set that equal to 0. So this, from here to here, is a trig identity. They're going to start making their ways into our lives. All right, a trig identity. And now we realize that we have a few of them. We have 0, pi over 3, pi, 5 pi, and that's all 5 pi over 3. These are all possible critical numbers. But I want to go to the poi. You've done this before. You can finish this one if you want. But I want to go to the poi, so I want the second derivative, which is going to be negative cosine plus 2 cosine 2x. Now, I'm going to have to do something here, folks. I'm going to have to do another trig identity. Hooray! So we get negative, this is an x, by the way. So we get negative cosine x plus 2, and I'm going